So it's my pleasure to introduce Dennis Sung from California Polytechnic State University. So Dennis is an associate professor of statistics and affiliate professor of computer science at Cal Poly. And Dennis is also senior data scientist at Google. So Dennis got his bachelor's from Harvard and also his PhD in statistics from Stanford University in 2015. And he has been Cal Poly and since 2016, first as an assistant professor of statistics and then as an associate professor of statistics earlier this year. So today, Dennis will tell us a little bit about a framework for probability and the simulations. Thanks, Dennis.
All right, thank you, Shaozhen, and thank you to all of you for inviting me. This is a real pleasure to talk to people, in across the pond in the UK. So I live in California. I'm a professor at the California Polytechnic State University, where I was a former colleague of Tony's. And today I'm going to talk about some work that I've done with my colleagues at Cal Poly, and it's about a Python library called Symbulate. And I think, and the reason I'm talking about sort of a software library is because I think the design of the software library has some interesting mathematical, statistical, and programming ideas in it that I hope you guys will find interesting. And if you're interested in learning more, a lot of my talk is based on this paper that my colleague Kevin Ross and I have published in the Journal of Statistics Education, and it's called Symbulate: Simulation in the Language of Probability. So you can look for that paper if you're interested. So I'm going to begin by just giving some motivation for why we designed this library. Yes, and I wanted to also mention that feel free to interrupt if you have any questions. You can post them in the chat. I'll try to monitor that if I can. But if I don't get to you, also feel free to, you can also interrupt me as well. Okay, so here's a simple little example, right? Suppose we roll two fair six-sided dice, and we're going to find the random variable x to be the maximum and y to be the minimum of those two rolls. And the question is, what is the covariance between x and y? So this is a problem that you might give, in an introductory probability class. And you might have students try to simulate this. So one thing that unfortunately not uncommonly happens when you ask students to simulate something like this is they'll write something like this. Right, they'll write R, this is R code, but you can imagine something similar in any programming language of your choice, MATLAB, Python. So they might write this. They might say, okay, well, for x's, I'm going to simulate 10,000 times. I'm going to sample 1 through 6 uniformly, two rolls with replacement, and then I'm going to take the maximum. And then for y, I'm going to simulate 10,000 simulations, and I'm going to simulate the minimum of 2 dice rolls, right? And then I'm going to calculate the covariance between x and y. And that's going to be my simulated value of the covariance. So what's wrong with this code? I think most of us realize that the problem with this code is that we've completely decoupled x and y. They're from separate simulations, so they're of course not going to have any covariance, right? So the covariance is going to be 0, but there might be some simulation noise. So if you want to do the correct code, you actually have to make sure you jointly simulate x and y. You have to repeat 10,000 times. And you have to sample, the 2 dice rolls. And then for the same set of 10,000 simulations, you got to apply the max, apply the min to get your x and the y. And only then will your simulation be valid for estimating the covariance between x and y. So you have to make sure they're defined on the same probability space. And so this is something that actually trips up a non-trivial number of students. A lot of students actually write this top code and don't understand what they did wrong because they feel like they did simulate the maximum and the minimum, but they don't understand the idea that we need to think about how these two random variables are defined on the same probability space. So that brings me to, I think, what the shortcomings of R and other languages that you might use to do probability simulations. They don't prevent you from writing code that makes no statistical sense, right? So the code that we just wrote, the incorrect code, made perfect sense from a programming perspective. Right? From a programming perspective, there are no problems. The code parses and it runs and it gives you an answer. But the problem with the code is that it doesn't make any statistical sense. And there are no checks that sort of prevent you from doing things that don't make any statistical sense. The other problem I would say is, especially for introductory statistics students, they're learning a new language, and that's the language of probability. They're learning how to manipulate these random variables, probability spaces, and so on. And the code, the simulation code that you have to write, doesn't very much resemble how the language of probability, the language of probability that we write on paper. For example, we have this like, you simulate the x and y, and then you have this apply x, y, and this is basically you get a matrix, and then this is an axis, and then you take the maximum over that axis. So there are lots of sort of programming details that are not really relevant to students who are learning probability for the first time, and you might think that they're trying to use simulation to gain understanding, not to confuse them even more, not to give them something else to learn. So as a result, if we're trying to teach students simulation in a probability class to help them understand the concepts of probability, they really have to learn two languages in parallel. They have to learn the language of probability that they write on paper, and they separately basically have to learn the language of simulation in the language that they're writing in. And that code that they have to write to do those simulations is unnecessarily difficult, right? It's not very difficult, but it's more difficult than it needs to be, is my argument. So what do we do in Symbulate? So Symbulate is a Python library, and we're also working on an R version as well. But what Symbulate does is it lets you specify simulations from probability models. So for example, the example I just gave above, you might start off by saying, well, I want to simulate 2 dice rolls. So we're going to set up what's called a box model. And a box model is just, just imagine a box with tickets in it. And so the tickets in this case are labeled 1 through 6. And we're going to draw 2 tickets with replacement. And that's going to be our probability space. So the first step is we define our probability space to be we're going to draw 2 tickets at random from a box with tickets labeled 1 through 6. Then on top of this probability space, we're going to define 2 random variables. So on the same probability space, we're going to define 2 random variables, x and y. And remember, a random variable is just a function defined on a probability space. So the second argument here is just once we simulate an outcome from this probability space, what function are we going to apply to that outcome to get our random variable? So in the case of x, we're going to take the max. In the case of y, we're going to take the min. And then to calculate the covariance, we got to simulate sort of their joint distribution. So then we have x and y, so that kind of reflects the way we write joint distributions. And we're going to simulate 10,000 draws of x and y, and then calculate the covariance. So hopefully you see that this code here much more reflects the way you would talk about probability if you were writing it down on paper. And so one thing that Symbulate does, so one problem with R is that it didn't prevent you from sort of writing code that didn't make any statistical sense. So I want to give an example, a concrete example of how Symbulate prevents that. So suppose you tried to do the analog of the incorrect code above, in Symbulate. So you would just basically say x is a random variable defined on probability space where we take the max. Y is a random variable defined on an identical probability space, but not the same one, right? And then we take the minimum to define y. If we try to do x and y dot sim 10,000 dot covariance, what's going to happen is we're going to get an error. We're actually going to get an error. It's going to prevent us from doing this simulation. It's going to give us the error that random variables have to be defined on the same probability space in order for us to be able to simulate them. And so this provides a check, for students, as well as some error messages and diagnostics to help them understand what they're doing wrong. So the main philosophy of this programming paradigm is that random variables, and actually, as we'll see, this actually extends to random processes. They are abstract objects that we can manipulate. Okay, so they're abstract objects that we can manipulate independently of their simulations. Typically, in a traditional programming language where you're doing simulation, the very first thing you do is you simulate the realizations and then you manipulate them. Here in Symbulate, we can actually manipulate these random variables, add them, compose them, without actually, we can manipulate them without actually simulating them yet. So as I said, the random variables aren't realized. We don't actually do any simulations until we actually call .sim. And then another big aspect of the library that is useful, especially if you're using this in a teaching context, is it provides automatic visualizations. So simulations can be plotted using using a universal function called plot. So once you do the simulations, you can just call .plot, and it will automatically determine the appropriate type of plot. So in the example above, where we're simulating the joint distribution of the min and the max of 2 dice rolls, if you simulate 10,000 realizations and you call plot on it, it will automatically realize that because you're looking at the joint distribution of 2 random variables, you should make a sort of scatter plot of the simulations. And you can see, the different outcomes that we get. We get a lot of repeat outcomes, right? Because these are both discrete random variables with not many possible values. But you see that x always has to be bigger than y. So these are our simulations. So one key concept in the philosophy of Symbulate, in the design of this library, is the idea of probability world versus simulation world. So I wanted to sort of give some intuition about this. So for probability world, right, so we're thinking about random variables as sort of abstract objects that we manipulate before we actually simulate them. So simulation is the very last thing we do. So suppose we have the following code, right? I'm going to define x to be a Poisson random variable. I'm going to find y to be a Poisson 3 random variable. And then I might want to do something like, simulate from the conditional distribution of x, given that x plus y equals 6. Right, so I can define this conditional random variable with this conditional distribution, and then simulate 10,000 realizations of that, and then call plot. Now, when I run this code, what's going to happen? Of course, I'm going to get an error, right? I'm going to get an error because these 2 random variables, x and y, haven't been defined in the same probability space, right? Of course, what we meant to say was that x and y are independent, but we have to be explicit about that assumption. If we don't make that assumption, we get an error because we haven't specified the joint distribution of x and y. So we have to do something like this. So this works in Symbulate. So you have to say, well, we want x and y to be independent. So we're going to explicitly assume that they're independent. That specifies their joint distribution. And now this code will run. And this code will generate a plot like this, right? So given that the sum is 6, the sum of x and y is 6, the distribution of x, of course, is some number between 0 and 6. And this is the plot from 10,000 simulations. So that's how you think about this problem in probability world, where you kind of define the random variables first, and then only at the very end, when you have what you want, do you actually do the simulation. So I said that there are 2 worlds. There's probability world. There's also a simulation world for thinking about this. So we have x and y. They are random variables, and we can, again, assume that they're independent. And now, instead of defining a random variable with this conditional distribution, what we're going to do is we're just going to go ahead and simulate x and y. So we're going to simulate 10,000 realizations from the joint distribution of x and y. And now what we're going to do, this might be more familiar to you if you're sort of used to sort of traditional programming, simulation in a traditional programming language. Then if you wanted to simulate, the joint distribution of, if you want to simulate the conditional distribution of x given x plus y equals 6, you have to subset, right? So take your x vector, subset it to the observations where x plus y was equal to 6. That gives you a subset of vector, and then you can plot that. And if you do that plot, you get essentially the same thing, right? It should be the same thing on average. So there's 2 worlds, and they're actually equivalent. They're just equivalent ways of doing the same thing. They just differ in when you do the simulation. In probability world, you do the simulation at the end. In simulation world, you do the simulation fairly early on, and then you do manipulations with the realized values. Okay. Another thing that you can do in Symbulate is one thing one fact about Poisson random variables is that the conditional distribution of x given x plus y follows a binomial distribution. And so if students are sort of doing this investigation, they do the simulation, and then they get this plot, they might want to check, that the answer really is binomial. So you can actually plot named distributions on top of any graph. So by just calling .plot on this distribution, we can graph the binomial distribution and check that our simulations match the theory. So I think one way to think about these 2 worlds of probability versus simulation world is to think of it as kind of like a commutative diagram, right? So you have probability world, and you can define random variables x and y, and using composition operations like addition and conditioning, you can define the conditional distribution of x given x plus y, and then simulate. Or you can sort of go the other way around, right? You can go the other way around, which is you can first simulate the joint distribution of x and y. So here are our x values and our y values. And then using sort of addition and subsetting, we can sort of get essentially the same type of result. The same type of result here. So for every operation in probability world, there's an equivalent operation in simulation world. And so the simulation world is probably what you're more familiar with, but probability world is kind of, I think, the novel contribution of this simulation philosophy that we've designed. So one thing you might be worried about is, now that we have this simulation world, right? Now that we're going back to simulation world, which is more like traditional programming, you might be worried that in simulation world, you can actually start writing code that doesn't make any statistical sense again, right? Here's an example of code that doesn't make statistical sense. You might say, x and y are independent Poisson, and then you might simulate, 10,000 realizations of x, and then you might separately simulate 10,000 realizations of x plus y, and we'll call that S, right? Then you might try to do something like x, and then subset that to the ones where S is equal to 6, right? You might try to do something like that, but that wouldn't make any sense because S and X were generated from different simulations. So you're not really meaningfully getting anything about sort of the relationship between X and S. Luckily, because the X and S came from Symbulate, Symbulate has memory. It remembers that the X and S came from separate simulations. So you will actually get an error. It will, again, give you a warning that you're doing something that doesn't make statistical sense. It says if you want to filter one set of results by another, they have to come from the simulation. So Symbulate is going to, again, do this check to prevent you from doing things that don't make sense, even after you've done the simulation and you have these values. Okay, so that's a high-level overview of kind of, I think, the philosophy and design of this library. I want to actually show some sort of cooler examples. I want to show how this extends to random processes. So we've been talking about random variables, which are fairly simple, but random processes are significantly more complicated. So my motivating example is, how do you simulate Brownian motion, right? So for those of you who know, Brownian motion is a process that is everywhere continuous, but nowhere differentiable. Its sample paths are everywhere continuous, but nowhere differentiable. And so what that means is that it makes it very hard to simulate the exact Brownian motion path, right? Because you can't just simulate it at a few discrete points and then interpolate, because the interpolation might be close because of continuity, but because it's nowhere differentiable, it's still kind of infinitely wiggly. So you can't really store the information about Brownian motion in a finite number of bits, right? Because it's nowhere differentiable. So the usual approach to simulating Brownian motion is what you do is you discretize, right? So you accept the fact that you're not going to capture the nowhere differentiability of the sample paths. And so basically you discretize time, and then you simulate just a random walk essentially. And the problem with discretization is, if I simulate this Brownian motion, so you can see I've discretized it, I show the points where I actually did the simulation. And this looks reasonably like Brownian motion, right? This sample path looks fairly continuous, but not really differentiable. The problem with this is that then if I take the same sample path and I zoom in on a particular region, then when I look at sort of this zoomed in region, it doesn't really look like Brownian motion anymore. It's way too coarse, to be Brownian motion, right? It's way too smooth between these points to be Brownian motion. So the problem with the usual approach to simulating Brownian motion is that the resolution is fixed. If you sort of zoom in, then the graph is no longer an accurate representation of what the process is like. So the question is, can we simulate Brownian motion at any resolution whatsoever? Can we simulate at like an arbitrary resolution? So for example, so this is how it would work in Symbulate, right? So you define your Brownian motion. So you define it with, this is just standard Brownian motion with drift 0 and scale 1. And then we're going to draw one realization from the Brownian motion. And so we're going to call this little w. And little w is actually a function, right? It's a continuous time function, right? So each realization of Brownian motion is a sample path. So it's actually a function of time. And it's actually a continuous time function. So you should be able to evaluate this function at any time that you'd like. So we can do, w of 0. We can do w of 1. And it's continuous. So we don't have to choose an integer value of time. So the w of pi, right? Okay, so we can evaluate this Brownian motion at any time we'd like. Now, you might wonder how we actually simulate these values, right? What we did not do is we did not just do the interpolation thing. We did not just simulate at a fixed resolution, discretize, right? And then just interpolate. We didn't do that because that wouldn't be accurate. That wouldn't truly be representative of Brownian motion. So just to illustrate this fact, here's the simulation of Brownian motion, and for now we've plotted it between time 0 and time 10. And now what we're going to do is we're going to zoom in on a particular part of that sample path. So now we're going to take the same exact Brownian motion, the same realization, and then we're going to plot it between time 3 and time 4. And when you zoom in on this region, you see it does match the general contour of what you saw in the sort of zoomed out plot, right? You can see it starts high and then it drops down and then goes back up again. So we see the same general contour, right? Starts high, drops down, and then starts going back up. But we didn't lose any resolution, right? When we zoomed in, this still looks like Brownian motion. It still looks nowhere differentiable, right? So we have just as much resolution as we did before. And if we zoom in further, now let's look at like the region between 3.5 and 3.4 and 3.5. Again, we zoom in, we can see that this graph that we plotted agrees with this function above, right? It agrees, but we get more resolution. We actually see that all the little wiggly aspects of it that we couldn't see in the more zoomed out plot, right? So this still looks like Brownian motion, even though we've zoomed in, by a factor of 100. We can also zoom out, right? So we simulated this Brownian motion, and we can also zoom out to go from time 0 to time 50. So what we had before is just between 0 and 10. And you can see again, this agrees with this graph here, but we see much more of this graph. So the question is, how do we manage to do this? Like in terms of like programming wise, we know that it's impossible to actually store sample paths of Brownian motion on a digital computer, right? It's not possible to represent all that information, right, on a digital computer. So how do we manage to do this where we could basically simulate Brownian motion at any resolution? It would always be consistent with itself, and we'd never lose any resolution as we zoomed in. Like how was this possible? So I want to talk about sort of the challenges of this in terms of implementing this. So how can we generate a sample path W that can be evaluated at any time t and yet remains consistent across repeated evaluations, right? That just reflects the fact that when you zoom in, what you see is still consistent with any plots that you made before. The solution is we don't really do it. So when you first simulate the sample path, when you first generate the W, we don't actually simulate any values of the Brownian motion, right? So we use a strategy called lazy evaluation. What we do is we say, we're not going to simulate any values of Brownian motion until you ask for it. And then when you ask for the value of Brownian motion at a time, we're going to store that value, and then we're going to make sure that all future simulations are consistent with the values that have already been simulated, right? So what does that look like? Okay, so we're only going to generate the value of W at a time t star, as needed, and then we're going to store the values of t star and any simulated values in these vectors, and we're going to call them t and w. And then when we go to generate new values at new times, what we make sure we do is we simulate from the conditional distribution of Brownian motion at that time, given all the values we've seen so far. So we want to make sure that the new values we simulated are consistent with the values that we've already observed. And luckily for us, with Brownian motion, there's a very nice property. We have, it's a Gaussian process. So, the joint distribution, if you all finite dimensional distributions are multivariate normal. So if you have multivariate normal, and you look at conditional distributions of a multivariate normal, you again get a normal distribution. So we can basically simulate from the right conditional distribution just by doing some linear algebra with the vectors that we've stored and the covariance matrices. And so basically, with all these random processes, a lot of the random processes, can't be represented. They're infinite, so you can't actually simulate them. So we use a similar lazy evaluation strategy to simulate from all sorts of random processes, including Poisson processes and Markov chains as well. So I've been talking a lot, so I want to make sure that that if people have questions, that they have a chance to ask. But it seems like there haven't been questions so far. Okay, cool. So now I want to do a little bit of case study. So extending on the Brownian motion. So I want to look at a process called Brownian Bridge, which is a process that's very useful in statistics. So the Brownian Bridge process, we're going to call it B of T, is defined. There's three different ways you can sort of define the Brownian Bridge process. One is that it's a Gaussian process. So it's a Gaussian process with mean function equal to 0, and its autocovariance function is given by the minimum of S and T minus ST. So one way we can think of a Brownian bridge as just a Gaussian process with some mean function and some covariance function. Another way we can define Brownian bridge is we can define it in terms of Brownian motion, right? So if you start with Brownian motion, W, then the Brownian bridge process is just W at T minus T W, the Brownian motion at time 1. A third way you can sort of define Brownian bridge is you can define it as, again, in terms of Brownian motion. So you start with Brownian motion, and then you say it's a process whose distribution is the same as Brownian motion, given that the Brownian motion at time 1 is equal to 0, given the Brownian motion is at 0 at time 1. Okay, so these are three different ways we can define the Brownian bridge process. And I want to show you how you can use Symbulate to simulate Brownian bridge using all three of these definitions, using all three of these characterizations of this process. So let's look at definition 1. So definition 1 just says Brownian bridge is this Gaussian process with some mean function and covariance function. So there's a built-in Gaussian process, and we're going to say the mean function is 0. The covariance function is the covariance function, and then I'm just going to simulate 50 realizations, okay, of this Brownian bridge between t equals 0 and t equals 1. Okay, so between t equals 0 and t equals 1, you can see Brownian bridge looks something like this. So it starts at 0 at time 0, and it's also 0 at time 1, and then it kind of wiggles in between, right? And it's most wiggly, at 0.5, so it kind of looks like a bridge. That's kind of why it's called Brownian bridge. The other definition of Brownian bridge that you can use is you can define it as Brownian motion minus t times Brownian motion at time 1. So how would we, go about simulating this using code? So again, we're going to define W to be Brownian motion. Then we're going to define t to just be a generic continuous time function. So t here, it's a function of t, right? So we're just going to define this to be a function. And then we're going to just define B, the Brownian bridge, to be exactly sort of how you would write it, as a formula. You would write W of t, so W is the Brownian motion, evaluate at time t, minus t times W of 1. So this exactly matches what we wrote down on paper. And then we can again simulate 50 realizations of that, plot it between t equals 0 and t equals 1. And again, we get something that looks pretty similar to what we had on the previous slide. There's also a third definition of Brownian bridge. The third definition of Brownian bridge is you define it sort of in terms of the conditional distribution of Brownian motion. So you look at Brownian motion, and then you throw out all the paths where W1 is not equal to 0. So you make sure you only keep the ones where the Brownian motion returns to the origin at time 1. Okay. And so we can also simulate this in Symbulate. So again, W is Brownian motion. And now to simulate Brownian bridge, we're going to use the conditioning operator, right? Which the pipe, just like the way you would write it in math. And we're going to condition on W1 being equal to 0. Now there's a little bit of a catch here, which maybe some of you see, which is that we can't actually condition on W1 being equal to 0, because W1 follows a normal distribution, right? W1 follows a normal distribution. That's a continuous distribution. So the probability that a conditional distribution is exactly equal to any value is 0. It's a measure 0 event. So we can't actually do that. That's not actually possible. So what we have to do is we have to kind of fudge this a little bit. We have to say, well, okay, if it's within epsilon, of 0, then we'll keep the simulation. So here I'm only insisting that W1 be within 0.1 of 0. Okay, so if it's within 0.1 of 0, then we're going to keep it, and then we're going to look at the conditional distribution of W, given that W1 is close to 0, is within epsilon of 0. And if we do simulation, if we do 50 simulations of that, again, we simulate that, and it again looks like the Brownian bridge process that you saw previously. So I wanted to just kind of show some other examples of things you can do with this library. So you can do things like Markov chains, so discrete time Markov chains. So here's a transition matrix, and you can have a initial distribution, and then you can define a Markov chain probability space with that transition matrix. And then this is a simple 3-state Markov chain. So your states are 0, 1, and 2. And if you plot it, it shows you what state you're in, over time. And you can define sort of complicated random variables using Python code, right? Using Python code. So this is kind of a weird thing, but you can try to count up the cumulative fraction of time spent in each state. So here I'm going to count up the cumulative fraction of time spent in state 1. So I define my my random process on that Markov chain probability space. I'm going to start off my chain at 0 in state 0, and then I'm going to simulate sort of 100 steps of this Markov chain. And what I'm going to do is I'm going to take x. X is my Markov chain. Y is going to store the cumulative fraction of time spent in that state. So x is my Markov chain, and then up to time I, I'm going to count how many times I was in state 1. I was in state 1, and divide that by I. So that represents the fraction of time that I spent in state 1. I'm going to store that in a new random process called Y, and then I'm going to simulate this random process Y, which represents the cumulative fraction of time I spent. So if I simulate 10 realizations of that and I plot it, what you can see is okay, it varies. We always start in state 0, right? But eventually, as you run the Markov chain long enough, it sort of converges to the what you would expect from the stationary distribution for that Markov chain. You can also define stopping times, right? So stopping times are a little bit more complicated, but ultimately they're just a random variable defined on a probability space, right? So we can take our Markov chain, we can define the first time in state 1, right? Which is like, given a chain, you can figure out when's the first time you were in state 1 by just kind of writing a for loop, and then returning the time if the state was 1. And now I'm going to apply this function to my Markov chain. That's going to give me my stopping time. That's going to tell me what time I was first in state one. So this is a random variable defined on a random process probability space. If I simulate 1,000 observations there, I get this distribution for the stopping time when I'm first in state one. And you can do like compositions of these things, right? So you can take your Markov chain and evaluate it at that stopping time. So that stopping time is the first time you're in state one. So if you think about it, if I take my Markov chain and I evaluate it at the time that was the first time it was in state one, right? X of t is always going to be equal to 1, right? X, the Markov chain at that time, at that stopping time, is always going to be equal to 1. If we do 100 simulations, we can see that. We can see that we're always in state 1 at that stopping time. So this is kind of a toy example. It's not real. It just kind of illustrates that you can actually do some quite complicated things involving random processes and stopping times. There are also Poisson processes. So Poisson processes are built in. A Poisson process counts how many arrivals, how many events you have up to time t. So in general, the sample paths are, it's a discrete valued process because it represents counts. It's continuous time because those arrivals could happen at any time. And you can see the sample paths of Poisson process are step functions, right? They're step functions because your counts increment by 1 each time one of these arrivals, each time one of these events happen. And so here's 100 realizations of the Poisson process. So one kind of interesting fact about Poisson processes is that if you look at the value of a Poisson process of rate lambda 1, and you evaluate the process at an independent stopping time, t, which is just generated from an independent exponential distribution, completely independently of the process, that follows n of t follows a geometric distribution, and the parameter depends on the rate of the process and the rate for that stopping time. So we can verify this. This is something that students can check by doing a little simulation for themselves. So we're going to define a stopping time, the random variable from an exponential distribution. Let's just say lambda 2 is 0.5. And then we're going to assume that the process and the stopping time are independent. We'll explicitly call out that assumption. And then if we look at n of t, and we have to add 1 because the geometric distribution, includes the one success, and you simulate 10,000 of that, you get the blue bars here. And to verify that it follows the theoretical geometric distribution, you can overlay the geometric PMF on top of the simulation. You can see the agreement there, and that shows us that this theory is true. So in the last section, I want to just talk a little bit about how we've used this library in our classes. So my colleague Kevin Ross and I both teach a lot of probability classes at Cal Poly. So we teach undergraduate students, and we use Symbulate actually in our probability classes. So the two classes that we've used them in primarily, one is for engineers. So this is a traditional class that electrical engineers take. And this course covers, probability up through Gaussian processes, Brownian motion, and the Wiener-Khinchin theorem. Okay, and these students they had some exposure to Python, and we only have them do simulations in Symbulate. So Symbulate is a Python library, so they had some familiarity with programming, but not a lot. Many students, were not very comfortable with programming. Another class is a class for stats and data science students. And so this is probability for stats and data science students. And this is more of your traditional probability class. It covers, probability up through the central limit theorem. And these students actually all had prior exposure to, Python and R. And this course, being a statistics class, we actually required them to do simulation in both R and Symbulate. So they have to sort of juggle two different paradigms for doing simulation. And so we used Symbulate in a number of ways in these classes. One was we used Symbulate during class, in our lectures, to demonstrate properties of distributions before proving them. So something like, the exponential stopping time applied to a Poisson process, that might be something, that might be a little exercise that we might do in class. But before we actually do the derivation, we might show them the simulation first so that they know what to expect. We also assigned the students labs that required them to write Symbulate code to simulate the answer to questions. And we also required them to write a simulation where they checked their answer to each homework problem. So that was something that I sort of came up with, which is like, to encourage students to appreciate simulation, we have them, do conventional homework problems where you're doing math on paper, but I basically required that every single student have to, in addition to have the answer, they have to submit a simulation as well, where they verify in the simulation that they got the same exact answer that they calculated. And they were also allowed to use this during exams to check their answers as well. So we don't have a lot of evidence of effectiveness here, but we did do some surveys, of the students to see how they felt. And so, students generally agreed that, so course 1 is the engineer class, course 2 is the stats and data science students. You can see that students generally felt that simulation was helpful. But also many of them felt specifically that using Symbulate, was actually helpful for them in understanding the concepts that we were teaching them. So then the main question that we wanted to know was, if you had to do it over, which one of the following would you most prefer to use? So we asked that. So for the engineering class, 78%, almost 80% actually said that they would prefer Symbulate over using NumPy or SciPy or R, right? So that was pretty good. Even in the second course, this is a class taken by stats and data science students, they're more comfortable with R. So you can see that 23% of them actually would prefer to use R over anything else. And many data science students, they're quite comfortable with basic Python. So, they maybe prefer to use basic Python, but still a majority of the class said that if they had to pick one, they would actually choose to use Symbulate. So the way we kind of interpreted these results is course 1 is kind of a terminal course in probability. So students don't really go on and take more courses in probability after that. And so those students overwhelmingly preferred Symbulate. In the second course, this is like the introductory course in probability for stats and data science students. They're going to go on to take more statistics courses, more probability courses. So they still prefer Symbulate, but we understand why they might prefer R or Python, because thinking about their future courses and their career options, they may prefer to get more work experience, more relevant work experience with Python and R. So in conclusion, I want to encourage people to try out Symbulate and give us feedback. So if you want to install Symbulate, if you've ever used Python, you're familiar with pip. Pip allows you to install Python packages. So you can just do pip install Symbulate. And it's built on top of standard Python libraries. So it's just built on top of NumPy and SciPy. So you do need those. You can't just use base Python, but most people who are doing scientific mathematical work, scientific computing in Python already have these libraries. It's also open source, so you can check out our code on GitHub. You can contribute to it, and then we also have a paper. Our paper actually has been published in the journal Statistics Education, and so you can also look at our paper there. So thanks a lot for listening. It's been a pleasure to share this with you, and I'm happy to take time to answer questions. either about Symbulate or, about my experience, teaching data science and statistics courses.
Thanks very much, Dennis, for this excellent talk. So do we have any questions from the audience? So you can ask directly if you want.
There's one in the chat, I see.
Yes, there's one question from Abdul Reza.
Yeah, so the question is,
yeah.
how much is the difference between the speed of simulation in Python with respect to other software? So I want to say that Python in general, so I will say that Symbulate in general is slower, right? So Symbulate, by trying to develop this sort of abstract framework that's like philosophically consistent, there's a lot more overhead, right? There's some overhead associated with that, and it is slower than if you were to use other software. In general, in Python though is not any slower than other languages. So Python, I would say the speed of if you were using NumPy or SciPy to do simulations, it would be as fast as R or MATLAB or any language that you might think about doing simulations in. So Python's not slower. Symbulate is a little bit slower because it has overhead associated with, for example, the checking, right? It checks whether your simulations make sense. And every time you do a check, that's going to slow things down. But Symbulate is built on top of these libraries in Python that are very fast.
So do we have any questions from the audience?
Hi, I have a question. That's okay.
Yeah.
Hi, I'm Hector. Thanks, Dennis, for the interesting talk and the tool. I have a quick question about what you said relatively early on when you compared simulation world versus probability world. And I was curious whether they are exactly equivalent, because it seems to me that the probability world is more sample efficient, unless you're doing something interesting with lazy evaluation. Because in one case, you're sampling directly from the conditional distribution, and in the other case, you're sampling from the joint and then just taking a subset of samples. So presumably you get better data out of probability world?
Yes, thanks for that question. That's a great question, and that was actually a detail that I actually kind of swept under the rug. But you are absolutely right. So one thing that will happen here is that when you do things in probability world and you define sort of the conditional distribution abstractly, and then you simulate 10,000 observations, you will actually get 10,000 realizations from that conditional distribution. So you will get 10,000 numbers here. If you do it in simulation world, if you go down the red path, you simulate 10,000 and then you subset. And when you subset, you may not have 10,000 simulations anymore, right? You're going to have fewer than 10,000 in general. So you would actually have fewer than 10,000 numbers here. So you're absolutely right. For this example with conditioning, probability world and simulation world will not give the same results. I mean, the results will be the same on average and in the limit as you do more and more simulations, right? But you're absolutely right that they're not exactly equivalent. This approach is guaranteed to give you, 10,000.
Is there any situation?
Yes, sir.
Okay, thanks. Is there any situation where you would prefer simulation world over probability world?
That's a good question. I don't, other than speed. So simulation world is I would say the way we normally think about these kinds of problems, right? Think about conditioning type, simulating conditional distributions. We usually actually do things in simulation world. So, and so if you're prioritizing speed, then you would want to do things in simulation world because that would be likely to be fastest. Probability world, can be slower, right? Can be slower because there's some overhead associated with kind of doing this conditioning abstractly.
Right.
Yeah. That answer your question?
I see. Yeah, thank you. That was very interesting. Thanks.
Yeah, thanks.
So do we have any other questions from the audience? So can I ask one? So actually it's an observation. So from your survey at the end of your talk, it's showing that there's no students from the second class want to use MATLAB actually. Do you
Oh,
know?
that's interesting. That's,
Yeah, because my limited understanding, like on MATLAB and Python, that they are relatively similar to each other. But the main difference is that MATLAB, so Python is open source, so you can use it for free. But for MATLAB, you might have to pay.
yeah. To be honest, I think this is just mostly because the students have never used MATLAB. So the reason there's 9% in the first class, this is a class taken by electrical engineers. As you know, electrical engineers use MATLAB a lot. So they've seen MATLAB perhaps in their other courses. For these, statistics and data science majors, many of them have never actually used MATLAB. I would say most of them have barely know what MATLAB is. There's been I guess, general, outside of engineering, in the US, there's been a general shift, away from proprietary software like MATLAB and towards open source software like Python. And so I think these students may be just less familiar with what MATLAB can do.
Sure, that's fine. Do we have any? Yeah, that's very interesting. So do we have any final questions for Dennis? If not, so we will stop this seminar here today. Thanks everyone for attending this excellent talk by Dennis. Thank you very much all.